Engeni's visualization library aims to make quantum algorithm development more accessible, allowing you to understand how quantum algorithms are built to perform useful computations. The block sphere is a 3D representation of a single qubit state, depicted as a vector inside a sphere. When quantum gates are applied, they rotate this vector, visually showing how the state evolves. This intuitive visualization helps you grasp the dynamics of single qubit operations. The state space visualization shows how quantum states evolve at every stage of a circuit. As quantum gates act on qubits, you can watch the coefficients of the basis states transform, building an understanding of the quantum algorithm structure step by step. Engeni's quantum library also allows you to view the mathematical representation of the state vectors and explore compact representations like phase disks, which provide insight into the circuit's evolution. Once you've mastered these visualizations, you can use them to build your very first quantum algorithms. For example, Engeni's library enables you to construct a quantum Bayesian network, a probabilistic model that reveals relationships between events and their likelihood of influencing one another. With these tools, you can track quantum state evolution, ensuring you grasp how each gate contributes to solving computational problems. You can also explore geometric visualizations like the Q-sphere, a powerful tool for visualizing multiple qubit states. The Q-sphere represents the state vector by mapping each basis state onto a sphere. The size of the points reflects the probability of the basis state, their colors indicate phase, guided by a color legend, and their latitude shows the distribution of ones and zeros. After building your quantum algorithm, the final step is extracting meaningful classical information through measurements. Measurements collapse the quantum state into classical outcomes, reflecting probabilities encoded in the state vector. In the quantum Bayesian network example, the outcomes are visualized as a histogram, clearly showing the possibilities of each possible result. Engeni's premium course also includes hands-on exercises to validate your knowledge. By working directly with code, you'll gain practical experience in solving quantum problems and building algorithms. Exercises are structured for hands-on learning, allowing you to write and modify code while receiving immediate feedback. Built-in tests will validate your solutions, and if there's an error, you'll see messages to guide your improvements. In the hands-on exercises, you'll use Engeni's algorithm library to efficiently construct quantum machine learning algorithms, like quantum neural networks. With pre-designed building blocks, you can focus on understanding key concepts and experiment with powerful quantum computing techniques without starting from scratch. Engeni's library also provides tools to evaluate the effectiveness of your quantum algorithms designs. Metrics like entangling capacity and expressibility for quantum neural networks allow you to analyze the trade-offs between complexity and performance, ensuring your algorithms are both efficient and effective. In the QML for Medical Imaging course, you'll explore cutting-edge quantum and quantum-inspired solutions for medical imaging. From quantum filters like edge detection to tensor network models that reduce complexity of classical machine learning, you'll tackle real-world challenges with innovative tools. Additionally, quantum algorithms for image classification and segmentation will help you address critical tasks such as identifying tumors or segmenting regions of interest in medical scans. With Engeni's premium quantum machine learning courses, you're not just learning, you're building. Let's innovate together.